Again, learners in the class. In the previous video, we had seen, we had looked at how we can get derived quantities from fundamental quantities. Now, there is a scenario where we are going to get quantities that will not have dimensions, and these quantities are called dimensionless quantities. Now, what is an example of a dimensional quantity? What is an example of a dimensionless quantity? If you get a quantity which has no units, maybe, which is not related to a fundamental quantity, then we say that that is a dimensionless quantity. And what are examples of dimensionless quantities? Things like pi, you find a whole number in a given expression. Such things will stand for dimensionless quantities. Now straight, let's look at uses of dimensions. Uses of dimensions. Dimensions. Now, we are basically going to look at two uses. Use number one, dimensions are used to check. We are going to use dimensions to check validity of equations. We are going to check whether certain equations are correct, or whether they are valid or correct. Two, we are going to use a dimension analysis. We shall use dimension analysis to derive equations. We are going to use dimension analysis to derive equations. So these are the two uses of dimension analysis that we are basically going to look at. So now, let's begin straight away with looking at showing whether certain equations are valid or not valid. Now, how do we know that an equation is dimensionally consistent? So we shall say that for a dimensionally consistent equation, the dimensions on the left hand side should be equal to the dimensions of on the right hand side. I've used the short form here. This LHS stands for left hand side, then RHS stands for right hand side, and we say the square brackets meaning dimensions. So we are going to show, when do we say that an equation is dimensionally consistent? We are going to say that an equation is dimensionally consistent if the dimensions on the left hand side are equal to the dimensions on the right hand side. Then another thing that we should we should have in mind, or we should know that the equations where we need to add certain terms to other terms. Now, in dimensions, for us to be in position to add up things, these things must be having the same dimensions. You add up things that have the same dimensions, adding and subtraction will always go with it at the same dimensions, and this makes or leads us to what we call the principle of homogeneity. We shall call it the principle of homogeneity. What is the principle of homogeneity bringing to our attention? It is telling us that we only add or subtract quantities with the same dimensions. That's what we call the principle of homogeneity. For you to be in position to add or subtract then those quantities must be having the same dimensions. That is what we should have in mind when we are approaching this particular topic. So we say we're going to say, how do we check for validity of an equation? Now let's begin with some of the equations we are familiar with. How do we show that a given equation is dimensionally consistent? But then another thing that you should know, not all dimensionally consistent equations are correct expressions. Be careful with that. You will realize that the equations, like we shall see here, from dimension analysis. Dimension analysis will show us that these equations are dimensionally consistent. But in real sense, when you look at the equation is a wrong one. So that one, we shall also look at it as it unfolds. Now let's look at example 1 here. Example 1. Show that the second equation of motion, of linear motion is dimensionally consistent. So this is that is our question. So this question is a tricky one. They are saying the second equation of linear motion. So that means we must be knowing that second equation of motion. That is precondition number 1 to answering such a question. So we write the second equation of motion. S is equal to ut plus a half at squared, where these symbols carry their usual meaning, where S is displacement, U is initial velocity, T is time, A is acceleration, again T is time. A half in this case is a dimensionless constant. A half has no dimensions. We are saying it is a dimensionless constant. Now, let's answer the question. We said that for dimensional consistence, comma, the dimensions on the left hand side should be equal to the dimensions on the right hand side. So this is my equation. S is on my left, meaning the dimensions of S are my dimensions on the left hand side. Then the whole of this term is on my right of the equal side. So it means the whole of these quantities are the quantities that are on the right hand side. So let's begin. We are saying that for us to be in position to conclude that this equation is dimensionally consistent, then the dimensions on the left hand side should be equal to the dimensions on the right hand side. Now let's look at the dimensions on the left hand side. On the left hand side we have displacement, or S. So what are the dimensions of S? We found out that the dimensions of S is a displacement, which is a length. So the dimensions on the left hand side are equal to L. Now let's look at the dimensions on the right hand side. On the right hand side I have U, where we said U is velocity, whose dimensions we earlier on found out that the dimensions of U is L per T times the dimensions of T, and so we are going to multiply that plus a half times the dimensions of acceleration that we got as L per T squared. Yes, those were the dimensions of acceleration. We said it was L per T squared times the dimensions of T squared, which is L squared. Now, we do a little mathematics here. This is L per T squared times T. This is T power 1. Now, when these have the same bases, we tend to add up the powers. So, -1 plus 1, we get 0. And anything to power 0 is 1. Therefore, here we have L. We move to the next quantity. This is L per t squared times times t squared. Now we realize that these two have the same base, therefore we just add the powers. Negative 2 plus 2, we get 0, and therefore here we have a half L squared. Now summing up this, this is 1 plus a half, we get 3 out of 2 L. Now, what is our conclusion? Our conclusion here is going to be that since the dimensions on the left hand side are equal to the dimensions on the right hand side, then the second equation of linear motion is dimensionally consistent. Now, someone might be wondering, now master, you say this is 1L, this is 1.5 L. How are they consistent? I said that such figures, 3 out of 2 is a dimensionless constant. It is dimensionless. So if it is dimensionless, it has no effect. It means it is true. This is length, this is also length. We ignore the quantity. The quantity here doesn't matter simply because we take this to be a dimensionless what? To be a dimensionless constant. Is a dimensionless constant. So that is how we conclude. So we have shown that it's true the second equation of motion is dimensionally consistent. Now, let's look at the second example. The second example, which equation can we show that? Let's look at, let's show that, we should show that the third equation of motion is also dimensionally consistent. And the third equation of motion is v squared plus u squared plus 2as, where those letters carry their usual meanings. Now, if these letters carry their usual meanings, let's begin answering. When we are answering, we did say that for dimensional consistency, for an equation to be dimensionally consistent, for dimensional consistency, the dimensions on the left hand side must be equal to the dimensions on the right hand side. Now let's look for the dimensions on the left hand side. The dimensions on the left hand side are the dimensions of v squared, and we say the dimensions of v squared, which is the velocity squared. These dimensions, this is L per t, but now it is squared, which gives me L squared per t squared. So those are my dimensions on the left hand side. Now, let me also get the dimensions on the right hand side. So you come here and you say dimensions on the right hand side should be equal to, we have u, so these are dimensions of u, which is velocity, which is L per t squared, plus the dimensions of, now 2 is a dimensionless constant. In this case, it is a dimensionless constant again. So this is 2 into times the dimensions of acceleration, which is L per t squared, times the dimensions of length. So let's open this bracket. This gives me L squared per t squared plus 2L times L. This is L squared. This times that. This is L per t squared. Now when we add this, we get 3 L squared per t squared. Now, these are my dimensions on the right hand side. Now, when I look at these dimensions, it is true they are the same. Now, we conclude and say that Cis3 is a dimensionless constant. Cis3 is a dimensionless constant, comma, the dimensions on the left hand side are equal to the dimensions on the right hand side, and therefore the equation is dimensionally consistent. So that's how easily we can go about checking the validity of an equation. But remember, I did say that not all dimensionally consistent equations are correct equations. You must take note of that. Let's look at a scenario that will bring it out more vividly rather than just talking about it and we do not show. We are going to write, this is example 3. You are going to say that, show whether the equation, the expression below is